All right, today we are starting section 7.4. We are going to simplify expressions with rational exponents. Simplify expressions with rational exponents. So our notes say another way to write a radical expression. Another way to write a radical expression is to use a rational exponent, which is an exponent that is a fraction. Okay, so we have a couple examples we're going to put up here. Oops, sorry. Use a rational exponent. So for example, the first one is what kind of root? A square root. So we would write this as 25 to the 1 over, what's our index for a square root? 2. So this becomes 25 to the 1/2. Let me write that a little bigger so you can see it. 25 to the 1/2 power. Okay, on the next one, we are taking what kind of root? We got a cube root. So this would be 25 to the 1 over 3. Notice that pattern. Our index is going in the denominator of the fraction. And on the last one, what do you think it's going to be? 25 to the 1/4 power. We get this all filled in? Okay, so we can change these instead of having radicals to having rational exponents or fractional exponents. Okay. Here are some other examples. So all of these little fractions are meant to be written more as exponents. It's just hard to get it to print that way. Okay, so if you want to rewrite it a little bit differently to make it more obvious, you can. Okay, so let's switch back and forth between the rational exponent and the radical form. If we apply what we just talked about on the previous slide, if we're raising this to the 1/3 power, that's like taking which root? The cube root. So if it makes more sense to you to think about it as a cube root, that's fine. If we're looking for a cube root, we're looking to make groups of 3. And if we break down 125, what does it become?
25 and 5 and 5 and 5 25.
Good. This one is actually a perfect cube number. So the final answer would be just the number 5. Do we need a radical anymore? No, because it was a perfect cube. Perfect cube. There's a group of 3. All right. Questions about that first one? Okay. So on the second one, there are 2 different ways to think about it. One way to think about it would be to change them into the radical form, because that's what we're used to doing. We're used to using the radicals. The other way would be to apply our properties of exponents. If we are multiplying the same base, what do we do to the exponents? For example, a simpler example would be if we're taking x squared times x cubed, what would we do with those exponents? Add them. Ooh. We multiply when we take a power to a power. We're multiplying the same base, we add the exponents. So 2 plus 3. So we could do the same thing here. The base is the same. It's 5 and 5. So we could add the exponents.
2, 4.
Hold on. How in the world do we add fractions? I heard somebody say 2 over 4, and that is most certainly not how we add fractions. It would be 1. 1/2 plus 1/2 is equal to 1. 5 to the first power is just 5. If you wanted to go the radical route, what kind of root are we taking? A square root. So the alternative way of doing it would be to take the square root of 5 times the square root of 5, which is the square root of 25, which equals 5.
So you can always do it that way too as well, right?
If they have the same radical, yes. Okay, if we're working with the same type of root, so these were both square roots, then doing it this way is always an option. We might get to problems where the denominators don't match here. That makes it trickier. That means we can't just use radicals. So we would have to do it this way. Okay, or we would at least have to get the radicals to match before we could change it. We'll get there. We'll get there eventually. If your radicals match, you can always put it in radical form and multiply them. So for this next one, that's what I would recommend. I think radical form is a good option. What kind of root are we taking?
Cube.
A cube root. So we have the cube root of 10 times the cube root of 100. 10 times 100 would be 1,000. And what is the cube root of 1,000?
100.
No. 10. You could use a calculator or you could break this down. 110, 10 and 10. Got cut off at the very bottom there, but okay, either way, we should get a final answer of 10. Now on number 4, we don't have the same base, right? We got a 2 and we have an 8. So even though we have the same type of radical, we don't have the same base, so we cannot add the exponents there. It's the same reason here we went to radical form. The bases don't match, you can't add the exponents. So let's go with radical form instead. What would radical form of this first part be? The square root of 2 times the square root of 8, which equals the square root of 16 is 4. Okay, so on a lot of these, the radical way is probably going to be easier for you. Eventually, we'll get more into where we have to add the exponents. But I wanted you to see that we did get the same answer either way on that one. A rational exponent may have a numerator other than 1. That number becomes an exponent. So the denominator still tells us what type of radical to use, a square root, a cube root, so on. And then the numerator becomes an exponent on that number underneath the radical. Okay, so if you want to make yourself a little note off to the side, if this is your fraction bar, the numerator is the exponent, the denominator is the index. Okay. So on this example on the slide, what type of root are we taking? What's our index? 2. We're taking a square root. Our denominator was a 2. You do not have to write a 2 if you're taking a square root. Okay, you can just put the radical. And then we would have 25 raised to what power? The third power. Now we should simplify this. Right? We should continue to break this down. If you wanted to, you could multiply out all those 25s. Instead, my recommendation is to write them out and start looking for groups of 2. Okay, if we're taking a square root, we look for groups of 2. What do we already have a group of 2 of? 25. We've got a group of 2 25s. This last lonely 25 is going to break into what? 5 and 5. So then we have a pair of 5s. Are we going to have anything left over? No. Everything either was part of a pair or broke into a pair. So what's going to come outside the radical? 25 and a 5. 25 times 5 is 125. Any questions about how we changed it from a fraction to a radical? Why we simplified it the way that we did? Anything at all? Are ready to keep going? Okie dokie. All right, just a more formal definition about rational exponents. If the nth root of a is a real number and m is an integer, then a to the 1/nth power is the same as the nth root of a. We've already looked at that. That was the first thing we looked at, where everything was either just the cube root, the square root, we just changed it. And a raised to the m over nth power is equal to the nth root of a to the m. That's what we just looked at on the last slide, where we talked about the denominator being the index and the numerator being the exponent. Okay, really, these two things at the very bottom say the same thing. It's just here we have the specific case of the exponent being a 1. We could technically write an exponent of 1 on that a, and it looks like the same exact thing. Exponent over index. All right, write the exponential expressions in radical form. Okay, the first one, number 5, shouldn't be too bad. We know we're going to need a radical. We know there's an x underneath the radical. We just have to decide what the index is and what the exponent on the x is.
Index is 5, exponent is 3.
Good. Index is 5. Exponent is 3. That's all we had to do. Convert it into radical form. On number 6. We've got a decimal, but we're not used to dealing with these decimals. We want it to be written as a fraction. So we need to convert negative 2.5 into a fraction. If you want, you can do this one step at a time. You could change it to a mixed number, and then you could change it into a fraction. Remember, when you change negatives into fractions from mixed numbers, do not treat this like a negative 2. Okay, there's a negative sign, and we're going to take 2 times 2 plus 1. So 5 over 2. A lot of people make the mistake of treating it like a negative 2. They end up with like 3 over 2 instead. Don't do that. If you need to, just use a calculator to help you. Most calculators can take a decimal into a fraction. If you need help figuring out how to do that on your calculator, let me know after notes and I will assist you. Okay, now that we have it as a fraction, we're ready to change it into a radical. We know we need a radical and a y. What is our index? 2. So it's a square root. Do we need to put a 2 out there? No, we do not. What is our exponent on y? A negative 5. Okay, there will come a time in your Algebra II career probably where the directions will state specifically that you cannot have negative exponents. But since we're not worrying about that yet, we won't do that on this problem. We'll just leave it there for now. Anything before we continue on? Okay, on we go. Now we are going to write the radical expression in exponential form. So we are going to go the other way. We know we need an A. We know it's getting raised to a fraction. So what goes on the numerator? The exponent or the index? The exponent. What's the exponent?
2.
The exponent on this A is a 3. Are we all okay with that? What is the index on a square root? 2. So A to the 3 halves. Now the way number 8 is written looks a little funny, but we could rewrite it as the 5th root of B times the 5th root of B. Okay, and then this becomes the 5th root of B times B. If they've got the same index, we can put them underneath the same radical. So this really is the 5th root of B squared. Okay, so even though they put the exponent out here, really it belongs underneath with the B. And this is the work showing why that's the case. Are we all okay with that?
Yes.
Okay. But that's not what they want. They want it in exponential form. So we need a B with a fraction. What's the exponent? 2 over the index. 5. So B to the 2/5. Questions about number 8? All right, here is a big review of our rules of exponents. This looks very small and condensed, but these are very important. So some of them we've already talked about briefly. If we have a to the m times a to the n, we're multiplying the same base. What do we do with the exponents? We add them. A to the m plus n. The second one, we have a power raised to a power. What do we do? Multiply. So we have a to the m times n. If you don't want to put a dot there, you don't have to. You could just write mn if you know that that's multiplication. If we have a product raised to a power, then every factor of that product gets raised to that power. So AB raised to the m is the same as a to the m times b to the m. The fourth one is possibly one of the most forgotten or most confused rules that we have. If we have a negative exponent, how do we write it as a positive exponent? So if it helps, off to the side, if I write it like this. Does anybody remember how we're going to make it positive? It's a little sad for me. We need to move it. So if it is negative in the numerator, which is what it is here, it would be positive in the denominator. So we flip it. Now it won't always be a 1, okay, like this. We put over a 1 to change it into a fraction because it was not already a fraction. The basic rule of negative exponents is that you move it to make it positive. So if it's negative in the denominator, it'll go to the numerator to become positive. If it's It's negative in the numerator, it goes down to the denominator to become positive. So I would maybe put a big star by this one if you're not as familiar with that rule. All right, the next one I think more people are familiar with. If we divide the same base, what do we do to the exponents? Subtract them. A to the m minus n. Top exponent minus bottom exponent. And that last rule is similar to the third rule. If you have a fraction or quotient raised to an exponent, you can raise both the numerator and the denominator to that exponent. We need to know these rules, love these rules, be able to apply these rules all the time. All right, so we are going to simplify each completely, which, it doesn't state it directly, but no negative exponents. We just talked about how to make them positive, so we're going to start using that now. Okay, it's okay to have a negative number, you just can't have a negative exponent. All right. On the first one, if we're not quite sure what to do in this form, we could switch it to be in what? The number can be negative, that's fine. So if we don't like the fact that we have a fractional exponent, how could we rewrite it? Using a... What were we doing on the whole front side of the notes? We were... A radical. Okay, that's what we just finished doing. It's just that we'll have more work to simplify after we put it under a radical. Okay, we know we need a radical. We know we need a negative 32. What is our index? 5, and our exponent is a 3. It is okay to take a odd root of a negative number. That's fine. It just means our answer is going to be negative. Okay? So, if you want to, you could think about this as the fifth root of negative 32 times negative 32 times negative 32. If that helps you. Let's just break down a single 32 off to the side here. If we break down 32, what do we get?
8 and 2.
Well, I heard 8 and 4 first, so we'll stick with that for now. And 8 breaks into
4.
2 and a 4. The 4s break into... Okay. If we're taking a fifth root, we're looking for groups of 5. What do we have 5 of?
2.
2s. So 132, one of them, well, in this case they're negative, so we probably should make these all negative 2s. Okay. 1 negative 32 breaks into 5 negative 2s. So for each negative 32, we can bring out 1 negative 2. Does that make sense? This negative 32 would give us a negative 2. This negative 32 would give us a negative 2. This negative 32 would also give us a negative 2. Are we all okay with that?
Good.
Are we going to have anything left over?
No.
No. Okay, each of them came out nicely to a group of 5. Negative 2 times negative 2 times negative 2 is?
Negative 8.
Negative 8. Questions about how we did that problem? All right, on number 10, instead of having our exponent written as a decimal, I would rather have it written as a fraction.
4, -3, -3, and 1/2.
Okay, this is 4 and -3 and 1/2, which we would change to 4 raised to the negative 7/2. Good. If you can go straight from the decimal to the improper fraction, that's fine. I'm fine with that. If you need to go to the mixed number in the middle to get there, that's also okay. Questions at the moment? Okay, so let's change it now into a radical. What is my index?
7,
Index.
2.
2. Index is from the denominator, so I'm taking a square root, and my exponent on that 4 should be -7. But we don't want, nor do we really know how to deal with, a negative exponent in this sense. So I'm going to leave my big old square root sign, and I'm going to change this into a fraction. I'm going to have a 1 on top because I'm treating this like a negative exponent. To make it positive, I put it in the denominator. So if I put that in the denominator, all that's left in my numerator is a 1. We have 4 to the negative 7th, 4 to the positive 7th now in the denominator. Questions about that? This is not the only way to approach this problem, but I don't want to overwhelm you with information at the moment, so we'll just stick to it. Okay, we can break up our radical. That'll help us simplify it a little bit because in the top, the square root of 1 is 1. Over in the denominator, we could multiply it all out, or we're looking for groups of how many?
2.
2. We've got a bunch of 4s down here. How many
7.
groups are we going to have? 3 groups of 2 4s. If it doesn't make sense, go back to writing them all out. That was always our backup plan. Right? 1, 2, 3, 4, 5, 6, 7 of them. Circle your groups. 1, 2, 3 groups. Okay, so that's 4 times 4 times 4 on the outside. What's left on the inside? A 4, the lonely 4 right here. Now we're not quite done with this. We can still continue to simplify. Are we all okay with how I got 3 4s on the outside, 1 on the inside? Okay, we had 3 groups of 2, and then 1 left over.
3 groups of 2.
Does that make sense? Okay. Ooh, that's not what I wanted. That's what I wanted. All right. So 2 things can happen now. We can take 4 times 4 times 4, and we would get 64. We can also take the square root of 4 and get a 2. So our final answer would be 1 over 128. We applied a lot of different rules there. Do we have questions about any of the steps? Okay. All right, on the next one, I'll show you the alternative way kind of setting this up. If we have a negative exponent from the beginning, which we also had up here, you can go ahead and rewrite the problem with a positive exponent right away if you want to. Can I erase some of number 9 so I can have some room? We're all good with number 9? Let's just take some of that away. Okay, if I were to put this over 1 and I just, first thing I wanted to do was get rid of that negative exponent, I could flip this whole thing down into the denominator so that I would have 25 to the positive 3/2. I just don't write big enough for this to look good. 1 over 25 to the positive 3/2. We all okay with that? Then it's like we just have the 1 over it the whole way through instead of getting that halfway through. If you prefer the way we did it on number 4, that's fine. Does not matter to me. That's what makes these problems easy and hard, so that there are multiple ways to approach them. All right, let's switch it into radical form now. What is my index? 2. So I'm taking a square root of 25 to the 3rd power. So we have 1 over square root of 25 cubed. The 1 over is just going to keep coming along. We technically have already simplified 1 over 20, or sorry, we've already simplified the square root of 25 cubed.
125.
Okay, it comes out to be 125. If you need a refresher on that, go back to where we had 25 to the 3/2 or the square root of 25 cubed and see how we broke that down. We made 2 groups of 25. The last 25 split into 2 5s. 25 times 5 is 125. So our answer should be 1 over 125. Questions on 11. All right, on our last one, we don't have to worry about any negative exponents, but we do need to flip it to be in radical form. What is my index? 5. So a 5th root of 32 raised to the 4th power. Okay, from number 9, we know that every 32 breaks into how many 2's?
5.
5. Every 32 breaks into 5 2's. Okay, so for every 32 we have, 1 2 can come outside. How many 2's will we have? 4 of them. 1 for every 32. We had 4 32's. We end up with 4 2's. Is there anything left over? No. So we don't need our radical anymore. 2 times 2 times 2 times 2
16.
is 16. Okay, again, if you're not sure about that one, just start rewriting these. This would be 2 to the 5th to the 4th power. It's another way of writing it. Okay, so we would end up having 4 different 2's that could come out. Questions, concerns before we continue? How are we feeling about these so far? One person feels good.
Good.
Nobody else has a pulse. Okay, we'll keep going. See if we can make this a little more interesting for those of you that are bored by what's going on here. All right. I need to clear the other ones because I write too big for this. So I need to make... All right, like I said, lots of different ways to approach a single problem. My initial suggestion is going to be to get rid of parentheses most of the time. The more of these problems you practice, the better you'll get a feel for your process with them. So if I'm getting rid of those parentheses, that means I'm going to apply this outside exponent to the 16 and to the y to the -8th. So I don't necessarily expect you to write this step quite as I would. 16 to the negative 3/4 times y to the negative 1/8 to the negative 3/4. Okay, that outside exponent gets put with both the 16 and the y to the negative 1/8. Now with the 16, there's nothing really to simplify just yet. Whereas with the y to the negative 1/8 to the negative 3/4, if we're taking a power to a power, how can I simplify that? A power to a power, what do we do? No. Multiply them. So we take negative 8 times negative 3/4. Negative times a negative is a positive. 8 times 3? 24 divided by 4 is 6. So that simplified pretty nicely right away. The negative's gone, the fraction's gone. Are we all okay with that part? Now we just have to deal with that 16 to the negative 3/4. Next thing I would recommend is making it positive. Well, be careful. It's not going to be 1 over this time. What's still going to be in our numerator? Good. Y to the 6th doesn't need to get moved, so it's going to stay in the numerator. But yes, the 16 to the 3/4 gets moved down so that its exponent becomes positive. What do you think I'm going to recommend we do next? I don't want to keep working with this fraction.
Yeah, so it'll be 16 to the 4th power. Wait, no, 16. It'll be. I can't say that.
What special symbol do we want to use? A radical. We want to put it into radical form now. There will be a 16 underneath the radical. Good. Our power is 3. Our index is 4. So when we break this down, again, I don't necessarily expect that you'll write it this way, but you can if you want. We're going to have 16 times 16 times 16. We're looking for groups of 4. So we don't have a group of 4 yet, but we can break down a 16 into 4 and 4. 4's break into 2 and 2 and 2 and 2. Okay. So we've got a group of 4 2's for every 16. Does that make sense?
Yes.
So how many 2's can come out?
3.
3 of them. 1 of them for each 16. 2, a 2, and a 2. Is there going to be anything left over? No. So we would have 2 times 2 times 2, which is 8. Again, that's not the only way to do that problem. Okay, from the very beginning, we could have rewritten 16 as 2 to the 4th power and gone from there. I just think that sticking with this method, it's a little bit more systematic. Any questions on 13 at all? Because in order to move on, I have to make all of this go away. Again, I would get rid of those parentheses first. 8 to the negative 1/3 times x to the 15th to the negative 1/3. Okay, so that power gets given to both pieces. If there were 3 different things in those parentheses, it'd go to every single piece. Okay, let's first deal with these parentheses now. We've got a power to a power, so we... Good. So x to the negative 5th. This time, both pieces have negative exponents. So when we rewrite it, What's going to be left in our numerator?
Nothing but a 1.
A 1. Okay, if both things have to move down, we've got a 1 left over in the top. So we have 8 to the 1/3, x to the 5th. Remember, when we move it, the exponent becomes positive. Okay, from here, this one actually is not so bad. We need to rewrite 8 to the 1/3 as a radical. What kind of root are we taking? Cube root of 8. That's still getting multiplied by x to the 5th. Should I put the x to the 5th under the radical?
No.
No. Don't do it. Okay, it has a whole number exponent. It is separate from the cube root of 8. So don't confuse yourself and do that on accident. The cube root of 8 is 2 with nothing left over. So we end up with 1 over 2x to the 5th.
Do we have to keep it over the 1 over it?
Yes, we've got to keep the 1 over it. It's a good question. If we didn't, we would be implying that the exponents are positive in the numerator, and that's not true. They're only positive in the denominator. Well, let's see if I, nope, down here. There's the last one. Okay. We've got one more. This one is not so bad. If we have a fraction raised to an exponent, then both the top and the bottom get the exponent on the outside. Okay, so this step I don't necessarily always expect to see, but we've got x to the 1/4 to the 12th over y to the -3/4 to the 12th. We give that exponent to the top and the bottom. Now, in both the top and bottom, we have a power to a power. If we have a power to a power, we do what? Power to a power, we multiply. Oh, so, right. So when we see fractions, sometimes we think we want to simplify top to bottom. Are we going to be able to simplify top to bottom on this one? No, because? Okay, x and y are different variables, so the bases are different. Okay, so 1/4 of 12 is 3, so we have x cubed over 3/4 of 12. What's 12 times 3? 36 divided by 4 is 9, and it should still be negative for now. But we don't want negative exponents. We want them to be positive. So move it to the top. Good. If it's negative in the bottom, it becomes positive when we move it to the top. Does that mean we should also move the x cubed? No. The x cubed was already positive, so it's going to stay positive, stay put. There's our answer. Yes, if you would like to put this over a 1, you can. You do not have to.